Hey everyone, my name is Boyan Krosnov. I'm a co-founder and CTO of StorPool Storage. My session is more of a technical deep dive into our technology as well as the more operational aspects of it. And then our last session will focus more on the value of the product, the value that we deliver to customers. So kind of going back to history, traditional storage system looks like this. You have a base array with two controllers and then expansion shelves, disk shelves. And the typical data center environment nowadays looks something like this. So you have like a leaf and spine network, what we call a data center wide network on the top that ends up on top of rack switches. And then within each rack, you have a bunch of servers. These servers tend to be identical. And there is this concept of a building block, which means when you purchase infrastructure, you buy a whole rack full of servers and switches. Sometimes the building block is several racks size because it is like a several percent optimization to go to several, like a pod instead of a rack. And some of our customers do that. And an important observation in that is that the traditional storage array doesn't really fit within the data center environment. And I'll explore a bit more why we think it doesn't fit. So first, in the building block concept, you have this issue of you don't have enough predictability. So if you have a storage array within the building block, which is what most people do, so, the building block is 20 servers and a flash array from a major vendor. 2 years down the line, you figure out you need more performance within that building block, or you need some more capacity in that building block, and you're stuck. It just doesn't, because it's a scale-up architecture array, there is very little you can do. The data center scale Ethernet network is not an A fabric, B fabric we know from fiber channel. It's just a completely different network architecture. So traditional arrays don't fit well into that. Our customers and many of these modern IT organizations run on what we call an always-on operational model, meaning there are no maintenance windows. The application is supposed to work 24/7. And any maintenance upgrades, resizing, etc., needs to fit within that model. If you have any,
hey Boyan, Boyan,
go ahead.
Why isn't the traditional array working within the building block concept of the data center?
Why doesn't it work?
Yeah, I mean, it seems like it works. It plugs into the top of rack switch and all that stuff, and
you can and people do that. It just has a lot of disadvantages, which are the ones I'm trying to go through now. One of the disadvantages is lack of predictability. So if you deploy today and 2 years down the line you figure out you need more performance, you run out of performance, and what do? You need to add a second array in the same building block, and maybe you don't have the rack units to add that array. For example, and there are bottlenecks at the controllers. So a lot of we hear from the market, from our customers, that in traditional arrays, running out of performance on the storage array and having to get, say, a second base array because you've run out of performance is very common, which is not in our architecture. If you need to do any form of multi-rack availability, so the ability to survive multiple racks being down and the application continuing to work, to support it with the traditional array, you can, but it means running kind of synchronous replication between two arrays, and it's more complex, more costly. It has a high system lifecycle cost, and the system lifecycle is not aligned with the rest of your infrastructure. So, you have the lifecycle of your servers, and separately from that, you have the lifecycle of your storage arrays, and they're not aligned. They're not the same thing. And also, so part of high system lifecycle cost is what do you do at the end of that lifecycle, and need to migrate data off, etc. There's slow adoption of innovation, meaning in traditional disk arrays, you don't get the kind of the latest network interconnects, storage devices, etc., because of the way these traditional arrays are developed. So you need to wait for the next version of the controllers, essentially. And they're hard to manage at scale. We'll go into that into a bit more detail. Most of the hard manageability comes from what we call data silos, or capacity fragmentation. So you end up with many small, say 100 terabyte to 200 terabyte pools of data, and each one of them is full to some degree, and you need to manage them. There's a lot of overhead to manage all of these separate silos. So in the beginning, when we started StorPool, we were looking at how would the ideal storage platform look like as kind of a target for us, what we should achieve. First, it must use commodity servers. If you use commodity servers, you fit within the kind of procurement model of your customers much better, because the building block ends up being, two top-of-rack switches and identical servers. You don't have two types of devices inside the rack. It fits in the data center design, including the modern data center network. So it's not an AB fabric. It's like a modern data center network. It fits in our customers' workflows and in their technology stacks. So if they use, say, for example, they use OpenStack, the solution needs to fit in the OpenStack environment. It's not enough for the solution just to provide iSCSI. It needs to be fully integrated in their whole business and workflow. It needs to address demanding applications. So we can't, when we design a solution, we can't exclude transactional databases, for example. We can't tell our customers, you know what, you should run transactional databases on local storage because the storage system is not fast enough. It's just not an option for us. It needs to be very efficient and extract a lot of the performance of hardware. It needs to provide data redundancy and data efficiency, but without a compromise on performance. So still get low latency, even though there are some kind of data redundancy, data efficiency capabilities in the system. It needs to scale. So it's not good enough to say, our system is going to do 200 terabytes, and then you buy another box and you do another 200 terabytes. It needs to kind of provide a large pool of shared capacity and performance. And lastly, it needs to fade into the background, which we explain as for our customers, instead of them spending time and effort in managing their storage solution, they should spend that time and effort into more profitable, more productive tasks. And we do that by eliminating, toil, eliminating hassle, and all kinds of things. So to achieve that, all of these goals for how an ideal storage platform should look like, you can't do it with the traditional architecture because the traditional architecture leads to all the negatives that I mentioned 2 slides back. And you need a radical departure. You need a from the ground up different architecture to solve these challenges, and a different way of delivering the storage solution, etc. And StorPool is that. StorPool has been designed from the ground up to address the challenges to be that ideal storage platform. Going into how it works. So you have a StorPool cluster, which is composed of a number of storage nodes. Within each storage node, you have SSDs or NVMe drives or hard disk drives. They're local. Very rarely we would use external enclosures. They're usually internal drives in a standard server. The cluster starts with 3 nodes and then grows up to infinity, to really large scales. And on each server, you have the kind of StorPool server services, the ones that take care of data on each individual drive, as well as a parallel iSCSI target and a parallel NVMe target. Parallel meaning it's deployed across the whole storage cluster. It's not like a single gateway. It's a very wide and parallel architecture on the front as well. And we have a highly available NFS service since somewhat recently to support some kind of limited file use cases. But our target is kind of the main target is the block storage, low latency, high throughput, high performance block storage workloads. The storage nodes are connected to a network that with sufficient bandwidth throughput, with sufficient performance, which could be 2 times 10 gigabit at the very low end, or it could be 4 times 100 gigabit at the very high end of performance density. Typically, it would be 2 times or 4 times 25 per storage node. And then on top of that, you have the workloads. So like, for example, a KVM hypervisor that might be running a StorPool client and might connect over the StorPool proprietary protocol, StorPool block, to the StorPool storage system, or it might also connect over iSCSI or NVMe TCP. You could have bare metal Linux servers running something like a large transactional database. And again, you could do StorPool native protocol, or you could do iSCSI or NVMe TCP here. You could have VMware, and in that case, again, iSCSI or NVMe TCP. Or you could have Hyper-V hypervisors, and we also have customers running some other kind of more unusual workloads on StorPool. In one way, you can think of it as, it's a block storage system. So, we provide a standard protocol iSCSI, and you connect your standard protocol workload on top. We are very kind of strong in supporting a self-service dynamically provisioned workflow in the KVM ecosystem. So things like in a service provider, a customer comes and they create a virtual machine of a template, and that ends up being a thin clone created in the storage system based on an integration between StorPool and OpenStack.
So, Boyan, does a LUN span multiple nodes?
Does a LUN span? I have a slide on that, but shortly, the way the volume is kind of partitioned into chunks, or call them stripes, and for each one of them, we select where it's placed in the storage cluster. So each volume ends up being striped across basically all the drives in the system. It's widely striped.
Okay. And what is the reliability of, because when you stripe it across multiple nodes, chances of failure increases by the number of node factor also. So how do you maintain the reliability of the volume?
I have special slides on that.
Okay.
So I'll delay that until I get to the data redundancy schemes slide.
Okay.
So Boyan, I don't see containers in this environment, Kubernetes or container.
We don't mention Docker and Kubernetes in the Linux bare metal. So we have a Kubernetes integration through the CSI, and that's suitable for Kubernetes bare metal deployments. If you're running Kubernetes in virtual machines, then a better way to achieve kind of dynamic provisioning, etc., would be to integrate Kubernetes with the cloud management platform. So say Kubernetes to OpenStack integration instead of Kubernetes integrating with the storage system. But for Linux bare metal, we do have a Kubernetes CSI driver.
So Boyan, question just so that I'm clear: the everything above that network diagram you've got here, that network line, right?
Yeah.
This is what comes automatically with your configuration, or are these, so could I have a KVM hypervisor and VMware only, or is this something that comes with the way your customer deploys it?
Those are the consumers above the line.
Yeah.
Okay. Oh, these are the consumers above the line. Sorry.
Above the line is the client.
Okay, gotcha.
Above the line is their task.
Okay, that was a little unclear to me. Sorry.
These are, to move on, these are the workloads that our customers run, and
got it.
All of the mentioned ones are supported workloads, meaning
Gotcha.
would help them with issues with them.
Okay. Okay, thank you. I wasn't sure.
What are your data protection algorithms or setup?
Triple replication, and we're looking at erasure coding soon, and I have a special slide on that a bit further.
Okay.
So StorPool consists of the StorPool Storage product, the core platform, and also metrics and analytics piece, alerts and reporting product, volume care, which is a snapshot scheduling, retention kind of tool that some of our customers use to develop and provide backup and DR services. And we have a number of integrations with cloud management platforms like OpenStack, CloudStack, etc. We'll focus on the core platform, and we'll talk about the architecture of that. And that core platform provides the block storage system provides very good latency and throughput. It's a parallel shared nothing architecture, which I'll explain in a bit. It's linearly scalable to large subclusters, or let's call them zones of capacity and performance. And then you could have multiple zones in a very large deployment in a very large system. And these multiple subclusters are under unified management. And that's how we achieve kind of data center scale deployments. So it's like two levels. One is you have zones with internal redundancies, synchronous replication, and then on top of that, you have common management across multiple of these zones. It has very good data management and kind of typical for some customers to keep hundreds of snapshots for every volume. And this data management functionality in StorPool enables backup and DR services that our service provider customers provide to their customers. And it supports data center scale deployments. I think I'm kind of repeating myself a bit. What does it contain? So within each storage node, there are a number of StorPool storage services, which you can think of as just programs or like processes in Linux. Beacon, taking care of kind of cluster management service discovery, server, and there will typically be multiple StorPool server instances per node, providing additional parallelism. So there is not only node level parallelism, there is a kind of drive level parallelism in StorPool, which store data on persistent memory on NVMe or SAS or SATA SSD hard disk drives using StorPool's on-disk format, which is our own kind of format of storing things in StorPool. And sorry, I'm trying to, okay. There is the block client, which is the client for the StorPool proprietary protocol. And there is also a nice SCSI target, an NVMe TCP target service, which is parallel across storage nodes. Bridge service is what provides kind of remote data management capabilities. So things like sending a snapshot from one location to another location is done through the bridge services. And management service, which provides a highly available API endpoint. As I mentioned, this is what happens within one storage node. And even within one storage node, there may be multiple of these services deployed.
What's a minimum number of nodes for configuration?
It's 3 nodes and 3 nodes with triple replication, and kind of the smallest deployment could be 3 nodes with 4 NVMe drives each, for example. These services communicate with each other using the StorPool protocol, and they're all built on top of the StorPool framework, which contains drivers for devices, network protocol implementations, memory management, kind of scheduling and tasks management, and a lot of kind of infrastructure work, which we've had to do. And the end result of, again, this is what happens in one storage node, and it's a parallel architecture, meaning you have many instances, many copies of what you see on the screen running in a system, in a cluster. End result is, of all this effort we spent on these services, is exceptional performance. So the results I'm showing now are with a relatively small storage system, starting from 12 NVMe drives and going up to 28 NVMe drives, and the goal of this is to show that performance scales with the size of the system. It's not like the more nodes you have, the more NVMe drives you have, the better performance you get. So for 4K IOPS, even a very small StorPool storage system with 28 NVMe drives gets 1.6 million IOPS, 7030 4K. 16K is 700,000 IOPS with the same mix. And across the same range of size of the system, you get consistently low latency, so like 100 microseconds for reads or 70 microseconds for writes. And these...
Where are you measuring that latency from? From within the storage box or from the host?
It's from 7 individual clients, which are separate from the storage nodes. So common question here is, how do you achieve 70 microseconds of write latency in a triple replicated distributed storage system? One part, there are multiple reasons, multiple ways in which help it. But one important one is the architecture within each storage node. So over here, you have the network interface card. That storage node is connected via 2x25 to the network. Then they have multiple StorPool server instances, and each one of them manages individual NVMe drives. There is no, in this architecture, there is no kind of contention between anything you see on the screen. So each server instance manages a particular NVMe drive. There is no like a server accessing a different NVMe drive and having to apply a lock, for example, or anything like that. So no contention. And also, there is kernel bypass between NVMEs and server instances, and also kernel bypass between server instances from network interface cards. Meaning, within that 70 microseconds, you can imagine the network operation going from the client to first server, second server, third server, and being committed to 3 NVMe drives, and the client getting a response. Along the whole path I described, there is not a single context switch. There is not a syscall. There are no syscalls in there. The StorPool server talks to NVMe drives and network interface cards directly, and that reduces a lot of latency that we would otherwise have in terms of scheduling or extra latencies for syscalls, etc.
So just to be clear, the performance that you attained was using your own block client?
Correct. So the numbers we showed were with StorPool block. The numbers we get with iSCSI are something like 30 microseconds more, I think. Yeah, about 30 microseconds more.
So, Boyan, I noticed on the previous slide when you were talking about what protocols are available for what kind of clients, things like VMware and Hyper-V, which is the bulk of the world, are only iSCSI and NVMe TCP today. Is there any...
Correct.
Are there any plans to bring block to those so we can get the lower latency numbers?
Not at the moment, no. So with VMware, it's kind of would be nearly impossible because we would need to convince VMware to put a new kernel, put our code in the VMware kernel. With Hyper-V, it might be possible, but there are no plans to do that at the moment.
What about plans for virtual volume, vVols?
Yes, there are plans for vVols. Sometime in the future, we're looking at it.
VMware needs to support vVols with iSCSI first.
I'm sorry?
VMware needs to support vVols with iSCSI first.
They do actually support.
So you have cores equivalent to or more than the number of NVMe drives in a server, so that you can create those many server instances, which also means thread, which would need their core, and you do association of thread to a core.
Nothing on this diagram is fixed or prescriptive, meaning in a deployment, depending on the design of the deployment and depending on how much performance you need, you could have a single server instance running on a single core managing tens of NVMe drives, or you could also have 2 server instances per NVMe drive. So it's kind of scalable in terms of how much CPU you allocate on top of the NVMe drives.
Okay.
Boyan, the other question would be, a storage node is a dedicated server in your environment. It's not like you could run other VMs on that storage node or anything like that. You're going to use complete server hardware resources to perform storage services, right?
Not in the KVM ecosystem. So with KVM, we do hyperconvergence. Maybe 30-40% of our deployments are hyperconverged with KVM, which is a way to say running virtual machines on the storage nodes, or vice versa, running the storage system on the hypervisors, right?
Yeah, and Boyan, hey, this is Max. Before we get into the data protection topic that you have here, I wanted to ask, regarding CPU, CPU types, CPU vendors and the specific optimizations. When I look at your website, you're saying that you can support AMD or Intel, but is there any of those, let's say, some of those CPUs have specific optimizations for storage performance and so on. So are you leveraging some of those?
We are on Intel and AMD. We also support ARM, by the way. I'd say we are not as optimized on ARM because of the kind of very small deployed base with that. But we leverage a number of instructor set as well as architectural capabilities of the Intel and the AMD platform to achieve the performance we achieve and the efficiency we achieve. Moving on, so for data protection, when we say 70 microseconds, right, that includes the time to replicate the data to 3 storage nodes and wait for the underlying drives to complete the write. Then the way it works is you have a volume. The volume is split into stripes, and for each 1 megabyte stripe, we select which drives this should be placed on. And it's a very fluid arrangement, meaning places where data is at the moment can be changed without disrupting the workload. So data can be moved around in the storage system without pausing or stalling the workload at all.
So Boyan, this placement of data via splitting it into chunks that goes on different nodes, is it a hash-based scheme, or it's more like a mapping scheme wherein... Yeah, go ahead.
Flexible map, meaning a table. And in terms of size of that metadata is minuscule, so it's not really the issue that some people imagine it is.
What's the max LUN size that we can support, like a single LUN size?
You could do a 1 petabyte LUN if you want. And we can go into more detail on a separate conversation if you want to dig into exactly how that works with a table-based or map-based kind of data placement.
Okay.
All right. Okay.
So just to be clear, so it's data is mirrored 3 ways. That's your data protection?
Yes.
Okay.
That's what we do today. And we're working on something better. And you'll hear more about it soon, I guess. All right. So another one common question when we talk about performance is how do you achieve this 70 microseconds write latency? Maybe you're cheating. Another common question is, and what about tail latency? Maybe you're telling me it's 70 microseconds average, and tail is like 10 milliseconds. So we did a performance consistency and tail latency benchmark in our lab, which goes like this. So we start with a system that is already running like a 50,000 IOPS per terabyte, 500 IOPS total load. And I have to note here that 50,000 IOPS per terabyte is like 25 times than the higher performance tier of someone like Pure Storage, right? So it's an extremely high initial load of the system. We will add on top of that QDEP1 transactional workload, random reads and writes, and we measure the latency, average and tail latency of this transactional one QDEP1 workload. And you get averages of 130 and 70 microseconds for writes, and 99th percentile of 360 and 100 microseconds for reads and writes, which we think is exceptional.
Before you move off that slide, I just wanted to, I'm assuming with those write latencies, that's actually hitting a write cache and not going to original media.
It is going to NVMe drives and NVMe, 3 NVMe drives actually. And the NVMe drives themselves have a power loss protected DRAM buffer, which the NVMe drive itself guarantees it will be committed in case of power loss.
Okay, so you're actually using cache inside the NVMe. Got it. Okay.
Yeah, there is no, like the hardware these systems are built on are an Intel or AMD CPU, an NVMe drive from Samsung, and a network interface card from Mellanox or Broadcom or Intel or someone. There is really no special hardware in these. There are no NVDIMMs, no DPUs, no nothing, right?
Okay, thanks. That was my question. Got it.
Yeah. Another topic is kind of multi-rack redundancy. If you deploy StorPool horizontally across multiple racks, you can achieve the system is still up if 2 racks fail because the redundancy is across racks and it's an N+2 redundancy scheme, which some of our customers do use. Then another topic, I'm just running through the topics now. Another topic is hardware refresh. So our customers have this concept of getting, like every 12 to 18 months, they have a new spec for the servers they buy, and then they buy identical servers after that. So they end up with, start with a cluster that's with the old hardware, and then they go and replace one of the storage nodes non-disruptively. Like empty out one of the old ones, get one new one, and over time they may end up for a long time on a mixed set of hardware, and that's supported, or they may end up with completely new hardware at the end of this. There are no data migrations. The workload is available throughout the whole process. The workload is not disrupted by these kind of emptying nodes or filling new nodes.
Another question on that. How do you actually do data location and rack awareness and that type of thing? How do you actually know to actually have the data spread appropriately? So if a couple racks go down, you're still okay.
So there's this concept of fault sets in StorPool, which by default is a fault set is one physical node, and it can be configured to be rack level fault sets, which means when we place the data, when we select where to place the data, we make sure that 3 copies are in different servers, and later with erasure coding, it would be a kind of data parity in different servers, right?
Okay.
Cool. You mentioned that you can migrate basically host by host there just to do the refresh. Yeah. How do you handle mixed topologies like that? Is it something where you can do this to do the upgrade, but the end result should be all identical hardware, or can you run mixed mode efficiently?
I'd say 70% of production clusters are with mixed nodes because they end up, you can imagine in like a longer time frame, in a 5 years plus time frame, these clusters end up with, say, 3 generations of hardware inside, and then you retire the oldest generation. Say they could be SATA SSDs and NVMEs today, and a year from now they could be just NVMe SSDs when they retire the SATA SSDs out, for example.
That's cool. Thank you.
So when you refresh hardware like that, and you're not forcing a data migration, then you're effectively rebuilding the data as you add a new server.
It's the same kind of one weird property of StorPool is recovery, data migration, as well. Rebalancing and kind of emptying a node, filling a node. They are all the same thing. They're all recovery.
Right.
We don't decrease the redundancy during this process, though, so it ends up being with 4 copies temporarily, and then it's back to 3 copies. Another kind of area of the product that we have built are integrations with CloudStack, Kubernetes, OpenStack, etc. I mentioned, and Volume Care. All of these, 6 separate software pieces run on top of the StorPool API. Volume Care is used by some of our customers to provide backup NDR services. So it gives you local snapshots and remote snapshots, scheduling and retention. That's kind of the scope of what Volume Care does. So what we do in terms of managed services, we get involved in design of the customer, making sure that the system we are offering, the system that's proposed, will solve the business problem, the business requirement. We deploy these systems using remote access, using our own automated deployment tools. Right after deployment and later in the process, we kind of fine-tune and measure, make sure the system we've delivered is of good quality as any other system we deliver. We, after it's in production, we monitor it and we react to alarms. We maintain these systems in terms of software upgrades, regular configuration checkups through a very kind of wide automated process. And it's a kind of closed cycle, and you go back to design for expansions or things like that. And the result is you get continuous service improvement with these systems that are managed.
Can I ask you one question as well on some of what you have here? You have Monitor there. Can you expand a bit on your monitoring and analytics capabilities, perhaps?
We collect a lot of metrics from our customers. We keep these metrics in a central metrics database, and we provide dashboards out of these metrics. So, for example, our customer can go in and look at the past performance of an individual virtual disk if they want it, or more widely. These are metrics for all kinds of things, so like CPU usage and network usage and individual drives and individual volumes and everything you can imagine from the storage system. And separate from that, we have unification of everything possible, but let's stick to the metrics for the moment because of the question. We also do, there are like, last time I looked, there are like 150 different alarms that trigger on different conditions. And the most basic ones would be a drive has died and needs to be replaced. And more advanced ones like these are kind of latency of user storage operations is higher than normal, and it may be visible by users. So maybe we need to take some action to react to it. And there are many of these that are documented in our knowledge base if you're interested, which is public. Moving on, so our managed services are enabled by metrics and analytics, unification of everything possible. So we try to keep all of these hundreds of storage systems similar to each other, even though they're deployed in different environments with different workloads. And on our customers' hardware, which tends to be not exactly the same every time. There are the events and alarms, and you get multiple channels for receiving the events to our team as well as to our customers' operations team, and that's Slack, email, web dashboard, etc. We have this concept of cross-immunization. If we find an issue, which could be any kind of issue, and not just like a bug in the software, the configuration issue, a bug in some firmware, etc. We make sure that that same issue doesn't happen in any other deployment of StorPool, and like all deployments benefit from the issues, the mistake of every other deployment. We have a lot of automation and tooling around that, which enables us to kind of maintain thousands of storage nodes with a relatively small team. And we have this hyperscaler-like approach to infrastructure, which the other things mentioned, but it's around these concepts of DevOps, continuous deployment, site reliability engineering kind of concepts. And to illustrate that, the oldest storage StorPool software running in production today is about 3 months old, meaning all production deployments of StorPool are on this rolling carousel of getting software updates, and the oldest one has been updated about 3 months ago. Meaning we do multiple upgrades per year. Moving on, I want to talk a bit about performance and why does performance matter. So people know high performance is important, but why is it important? Because higher performance means higher density, meaning you can achieve more with fewer storage nodes or in a smaller footprint. It also means fewer servers, fewer compute nodes. If your application is waiting less for storage, you can do more with that application on the same compute server, meaning you could get fewer servers, and it leads to a higher overall efficiency of the cloud. Bottom line is less hassle and fewer people involved. And by less hassle, I mostly mean a lot fewer performance. So storage admins don't get called because an application, a user thinks storage is too slow, because it isn't too slow, right? And it can handle, say, 10 times more performance than another system that the application developer is used to. And lastly, I have, to support the previous point, we have a case study with our customer Namecheap. And Namecheap says they achieve a 60% higher application density per rack. So they're supporting, say, previously they supported 100,000, and now they support 160,000 customers per rack in their data center. And that also goes with the number of servers and the power consumption. And they did that by using StorPool. Meaning, even though electricity prices in the US are 2 times higher, Namecheap is still paying less for energy than they did before adopting StorPool. And I'm going to close with a short summary of what we talked about. So StorPool is a parallel scale-out architecture which gives you exceptional performance and exceptional performance scalability. It is an always-on operational concept, meaning no maintenance windows, no waking up at 2 a.m. to do maintenance, none of that. It has no silos, so you don't run out of space because you're managing a much larger pool of capacity and much larger pool of performance compared to traditional storage arrays. And it's automated both in terms of say deployment of automation upgrades, as well as in terms of supporting a self-service dynamic provisioning workload. And operationally, for our customers, support and operations people, it means no toil, no repetitive tasks, and no hassle from having to deal with performance issues or a lot of the other issues we eliminate with what we do.
Do you have any other customer reference stories? I think I saw that second to last slide.
There are a bunch. So I can mention Namecheap, Dustin, Atos, Mito and Pulsant in the UK, Crystal, which is a UK-based cloud service provider, Cloud Sigma, which is a global cloud service provider, etc.
Okay.
Hosted an L and MSP in the Netherlands. There are a bunch.
Okay, thank you.
So Boyan, you mentioned volume care, snapshots, DR, and backup. Mm-hmm. Is that a separate service that you're offering, or is that something that's integrated with bundled with the basic StorPool? And are you considering snapshots to be the backup target in this sort of a discussion? And with DR, do you do, let's say, call it cross-cluster replication kinds of things?
One by one. So volume care is a separate software project, but it's delivered, like it's included in the price. It's part of the package. We don't price it separately. It is like snapshots, scheduling and retention kind of tool, which some of our customers have used to build backup and DR services as a service, like a cloud service provider. When they sell a backup service to one of their customers, these backups might be snapshots in a different location. StorPool, the core platform, even without the volume care, is capable of creating snapshots and capable of sending snapshots to different locations, creating, say, a clone of the snapshot and starting a VM of the clone. This is all supported by the core platform, and volume care just provides a bit of kind of orchestration on top of these core capabilities.
And so that sort of cloning activity would be what I consider asynchronous. It's not synchronous at a write level or anything like that.
Yes, it's snapshot-based replication, and depending on kind of the bandwidth, the link between the data centers, you may be able to do that very frequently, but it depends on kind of how far the link is between the data centers.
And so, it supports one replica, or does it support multiple replicas in like 3 sites or 10 sites, or
one to many and many to one and many to many?
One to many, many to one, and many
all of them. So there is no kind of
data flying everywhere.
For example, kind of to illustrate how flexible it is, we have customers that do in one location they have VMs and they send snapshots of these VMs to a second location for DR purposes, and at the second location they have VMs running all the time and they send snapshots of these to the first location. So both locations
cross-site replica,
primary and secondary, and there is nothing preventing them, for example, nothing stopping them from having a third location which is just a copy of the data, just backups.